Do you have any comments, questions you want to share with the class? Have you been joining the help sessions on Friday, any of you? Okay. Yeah. So I interpret this as everything going smoothly, which is nice. Yeah, so I guess I started recording already. Yeah, so today we are going to continue working with GeoPandas, and things are getting more and more interesting as we progress during this course. So today we are going to work with a number of things, as you can see on the course's website. So we will start by geocoding. And then it's like, this lesson is nice in a way that we take the steps and we work toward the final goal. So each of the parts of the lesson is needed in order to do the final step. So it's an example of how we can solve a geospatial problem. So it's a good practice in that way. Yeah, so we will start with geocoding, and we will talk briefly what we mean by geocoding soon, and then we will work, we will see how we can do geocoding using GeoPandas in Python environment. And once we are done with the geocoding part of the lesson, then we continue seeing how we can do different kinds of spatial queries, for example, to see whether a point is located inside a polygon, like this kind of spatial queries, which are important in GIS, also intersection. And then at the end, we will continue working with what we did in the geocoding part, and we will do a spatial join, which is again another important thing that we often need when we're working with GIS. So before I get it started, like those of you who came a bit later, we have this tiny microphone that you can use when you're talking if you want, but you don't have to if you don't want. So I have written 3 terms here that I'm sure you have heard about, but to some it might be a little bit confusing. So do you already have a clear idea what these things are and how they're different? Because we are going to work with geocoding today. I just want to make sure that you know what these are so you don't confuse them. So does anyone know what is geocoding? Do you want to be on the mic or not? Yeah. Okay.
Hello. I think geocoding is when we try to analyze spatial relationships of different data. For example, when we look at intersections or clipping or merging stuff.
Mm-hmm. Good try, but not exactly. Does anyone have any other idea? Yeah?
Yes.
Okay, I don't know. Do you want the mic?
Yeah, sure.
Yeah.
I think it's when you change like location attributes to like coordinates, like to direct location attributes, like for example post codes or
Yeah. Okay. Does anyone else anything to add? That's already a good definition. So geocoding, what we will be doing first thing today is just converting, like translating addresses, postal codes, whatever, name of places into coordinates. And that's a very useful thing. We will see an example of how we can do that. But imagine you get your data from a survey, like for example, it's a survey done by HSL or by some other organization, and they have asked where people go or where they live. So you have the addresses of people, but not coordinates. And imagine you want to do some GIS using this data. So how can you do it? GIS analysis on COMPI. You would need to know the coordinates of COMPI to have it in your GIS. So that's what we mean by geocoding. But what are these 2 other terms? We are not going to go there, but just to clarify the terms. What is geolocating? Any ideas? Geolocating is measuring the location of something. So in geocoding, you don't have a device, you have data. You're attaching coordinates to your data. In geolocating, the device or the system you're using is capable of locating you. So you probably have seen the example when you open Google Maps or some OSM or some web map, it asks you, do you want to be geolocated? And once you say yes, it shows where you are. And that's done using the IP of your computer or your device. It can be done using whatever, GPS, depending on what machine you're using. So that's geolocation. The system, the machine you're using is capable of identifying your location, and that's called geolocating. And then we have geotagging. Any idea what that is? Yeah?
When you have, for example, data of public transport users or social media users, and they're geotagged with the location, for example, movement from A to B.
Yeah, exactly. So geotag means that you have some kind of data, some attribute data, social media data. For example, you have tweets made by people, and then it can be tagged with location. So the main thing is that attribute data or that tweet, but optionally, very often it's optional, it can be tagged with location. So you know where that tweet has been made from, or an Instagram post or whatever. So that's the difference between these terms, but today we are going to work with geocoding, and now we know what we mean by that. Yeah, so by the end of this lesson, you should know how to geocode addresses. That's the first thing we will do today. Then we will learn how to make a spatial queries, for example, whether a point is in a polygon or not. And then we will do some spatial join to join different vector data. So yeah, so before we get started, I want to, we have a problem that we want to solve here. And forget about Python. Let's imagine that we are using the good old QGIS or whatever software you're more comfortable with. And how I want to know how you would approach this problem. How would you solve this? So you have a bunch of home addresses. You have gotten it from somewhere. So you know people live in, like, you have 200 rows of data, and you have addresses of people. And your question, the question you are trying to answer is, how many people live around that home location? So you basically want to see how densely populated these areas are. So you have been given a data set of home addresses, and then you know probably you can get population data from Python or other open data sources. So these are the data sets that are available to you, the population grid and the home addresses. So in QGIS or whatever software you're most comfortable with, how would you try to answer this question? Does anyone want to say something? Yeah.
So what was the question again? What are you trying to find out?
The population density around home locations. And home locations are in form of addresses. So you have been given a CSV file, a spreadsheet file with addresses.
So when we have the population grid, is it a vector data set?
It is vector, yeah.
Okay, then we can do a spatial join to find the home locations, like when they're in the same coordinate system like the population grid. Then they're going to be attached to a certain grid or polygon, which then has the information about the density. And then we have those kind of linked in the attribute table to each other, like spatially.
Yeah.
And then we can query the density based on the address point.
Yeah, exactly. Does anyone want to add something? Yeah, so that's a good answer. That's how you would do it. You have your spreadsheet. First of all, it's addresses, so we geocode the addresses to have coordinates, and then with the coordinates we can import it to GIS. In our case, it will be Python, but whatever software you will be using. And then you will do a spatial join. So you will get your population grid. In Finland, we have this population grid. It comes in different resolution. For example, we can publicly access this 1 kilometer by 1 kilometer grid. You do a spatial join. You get the attributes from the population data to your points, and then you can just calculate what you want. So this is basically what we are going to do today. We have a CSV file of addresses in Helsinki, and we want to do a number of calculations based on that. So let's go to our notebook environment. I have already pulled the latest changes, so you should have lesson 3. So if you haven't done that yet, do it now. But geocoding. So we already know what is geocoding. There are different services how we can do that. So Esri ArcGIS has its own way of doing that. We are very familiar with, for example, Google Maps. You just put name of a place, a country, a city, an address, name of a landmark. Then just Google Maps can pinpoint that place and you can get the coordinates of that place. You can do the same thing pretty much with all the online mapping systems, like with OSM or Baidu Maps or whatever is out there. So they have their geocoding system. Also, organizations like different countries have their own local versions. So I guess in Finland, at least HSL has its own thing for geolocating addresses and name of places. So there are a number of services. Some of them are publicly available. Some of them are not. But with all of them, there is an API using which you can communicate with the service. So you send a request, say, okay, I'm interested in knowing the coordinates of, I don't know, physical building in Kumpula. And then that sends you a response. So, but for us, we are already comfortable with Python. We are doing things in Python. We have learned how to work with GeoPandas to do things. So it would be easy for us if we can communicate with those services from our Python environment so that we don't have to like go back and forth. And luckily, there are libraries that can do that for us. So you do not need to use the API of Google Maps or whatever service you are interested in using for that purpose. So there are a number of libraries that can do this for us. One of the most popular ones is a library called GeoPy. There's a link here, so if you want to check out the documentation of library, you can do that. But again, a good news for us is that GeoPy is built in GeoPandas, similar to many other things we have seen. So we saw that, like for example, Shapely or PyProach. Many libraries come with the package of GeoPandas. It's the same with this library. So if you want to geocode, you don't need to even install a different library. It comes with the GeoPandas package. So the good thing about GeoPy is that you can do everything in Python environment. It works with GeoPandas. So what you get as the output is a geodata frame that we are familiar with. So it's very easy to work with it. And it works with different services. So we will see soon how we can work with it. But you can use GeoPy to use different services. For example, you can use it for Baidu Maps. Or what we will see today is that they will work with OpenStreetMap nominatim today. And it works nicely. So one thing about different services, so depending on your need, you may end up using different services. Well, one of the main factors is the limitation. So not all of them are free to use. For example, with Esri ArcGIS, you need to have license to use it. So that's one thing. You may not have access to all of them. Other thing is that some of them might be free partially, but there are limitations with them. So some of them have a quota, like how much can you use per day or per hour, something like that. So if you have a large data set, not all of these options might be available to you for free at least. Another thing that many of these have is a rate limiting. So if it's a free version, for example, they limit how many requests you can make to the system, for example, per second. Now, today we are going to use nominatim that works with OpenStreetMap, and the limit with that is 1 request per second. So you can get 1 address geocoded per second. So imagine if you have a very large data set of thousands of addresses, it will take quite a bit of time to do that. But one thing is that, of course, many of these are commercial, so they want to make money, but also this whole process is very heavy. Because imagine OpenStreetMap has a huge database of all the places around the globe. So if you're looking for one particular place, it's like it has to search for that in the database. So it's quite an expensive process to do. That's why they have these restrictions, other than the fact that many of them are commercial. So yeah, so today we are going to use nominatim, working with OSM. GeoPy, many of these services have, all these services have different requirements in terms of parameters you need to provide. Many of them actually need you to have an account. So you will have, for example, a token code that you will provide to the system so that they can bill you, they can check how much you're using. One good thing about nominatim is that it doesn't require that. So we do not need to sign up or generate any token code or anything. You can just say who you are, whatever name you provide as the user agent, and you can use it. So that's another factor. And for this course, of course, it's good so that we do not have to create accounts. So yeah, so that's what we are going to use today. And there are a lot of links to documentations, because as you can imagine, all these services have different requirements and they work differently. So if you want to use them, you should read the documentation. But let's get to CSC Noppe and start with the first notebook file, which is this geocoding. So we have a data set that we can check already here. It's under data, Helsinki addresses. It's a TXT file, it's CSV, comma separated. So you can see we don't have much in the data. There are just two columns. We have an ID field, and then we have the addresses. And you can see the addresses are in Helsinki. Yeah, so the addresses have the address, the postal area, and city, and the name of the country. So this is the data we are working with, and you can see there are 34 rows of data there. So as usual, let's start by using the pathlib library to define the path to our data directory. The code is typed in. Let's just run the cell. So the second thing we are doing is to read the CSV file we have. As you saw, it's not a geodata frame yet. We don't have coordinates, so we are just using pandas to read the data frame. So yeah, so the data we already looked at the data. It's under data directory, Helsinki addresses, addresses.txt. So we are just using good old pandas to read our data frame and look at the head of our data. We already saw the txt file. Here it looks a bit better. We have two columns, ID fields and the addresses. So now we are going to get started with the fun part, which is geocoding the addresses using a geocode function that is provided by, that is already available through GeoPandas library. So with Nominatim, as I said, all these services have different requirements. For Nominatim, again, you can check the documentation, but what we need is a user agent, and that can be any string. You can put your own name, whatever nickname, it doesn't matter. So let's start and see how we can geocode these addresses. So I will start importing our library, GeoPandas. So what we get as output from this geocoding process is a geodata frame. So you can decide how you want to name that. I'm going to name it geocoded addresses. And this is how you can access the geocoding function from GeoPandas. So under GeoPandas tools, there is a function called geocode that takes care of the geocoding. The next thing you need to provide is the column in your data that contains the addresses. So this was the name of my data frame, which we already loaded. And the column that contained the address information was named ADDR. If you're not sure, you can just check here. So it was ADDR. So that's the column that we have the addresses in. And most of these services are quite smart. So even if you're not super detailed about addresses, unless there's the same place with the same name many times in the world, they do a good job of understanding how it works. But of course, in the documentation, they say exactly how you should have the addresses so they can so it can understand it better. So the second parameter we are providing is the provider. So what service are you going to use for geocoding? So this is the parameter we provide, provider. And we are going to use Nominatim. So if you're using other services, of course, you put different names here. But now we use Nominatim, which is the OSM's geocoding engine. Then, as I said, Nominatim needs a user agent. You can put your name, a nickname, anything you want, doesn't matter. Just don't put the same as me, so it's not the same user making many requests at the same time. So I'm just going to use AutoGIS 2024, but you use something else. And that's it. I would also like to take a look at the output, so I'm going to just get the head of the output. I'm just copying the name of my variable to see what is the head of the data like. So once you're done, if you don't have any typo, just run this to see what you get. Okay, so these might work. Did anyone get output or did you get this error? Error message. Did anyone get the output? Yeah, for some of you it might work, depending on when you're doing it. Now there are many of us doing this at the same time. So you get timeout error. So it means that it is waiting to get a response. I don't know what's the exact value, 1 second, 2 seconds. If it doesn't get the response within that time, you get an error that it has timed out. So if that happens to you, you can provide one extra parameter here, and that is called timeout. And I'm going to give 10. You can give another value. And let's run this again. So what this is telling the Nominatim is that if the process took longer than 1 second, if it took up to 10 seconds, do not produce any error. Just wait until you get the response. As I said, this is a heavy process, geocoding, so it can take long, also depending on like how many users are using it at the same time and many other factors. So now because we said Nominatim, you can wait up to 10 seconds, so it can take a bit longer. Because we had 34 addresses, it might take up to 10 seconds to get each of them geocoded. So it can be easily like 300 seconds. But let's wait and see how long it takes. Did any of you get the output already? No. So last time I tried this, it took just a few seconds. Now it's taking longer. So how many of you have gotten the output already? Yeah, a couple of you. Yeah, okay, mine is ready as well. This is always the most exciting part of these lessons because we are going to use this for the rest of the day. So if you can't get this, I don't know how we will continue. But we got it now. Yeah, so the addresses are geocoded, and this is the output, geodata frame, which we are very familiar with. So we have a column added called geometry, which stores the geometry of our points. Yeah, so, and the addresses are there. So that's how it works. We had 34 addresses, they were geocoded. As you can see, it can take a bit of time. So if you have a huge data, then you might want to use another service. Yeah, so one thing that happened is that we don't have the ID column anymore, and there's no surprise. What we provided to the service was only the address column of our data, so the ID field is not there anymore. And this can be a problem if you have a data set that has many attributes, many columns, and then you geocode it, part of it is dropped, but we know that it's easy to get it back. We can just easily join it with the original data to get the ID field back. So one problem, which is easy to solve, so it's not a big problem, is that we don't have an ID field. So if you want to join this with your original data, like in QGIS, in ArcGIS, when you want to join, you have a common column, you use it for joining. In this case, we don't have that column anymore in the output. But the good thing is that the data is processed in the same order that it was provided to the service. So it reads it from row by row. So the output is in the same order as the original data. So we can use the same order. We can use the index field of our data to just join it with the original data. And that's what we are going to do next. So we already saw in the first, well, most of you have taken the first course, and we saw a couple of ways of expanding our data, so combining different data sets. So for example, you worked in one of the lessons, we worked with like concatenating, so appending more rows to our data. That was something we already saw. In one of your exercises, in exercise 6 of the first period course, we worked with, I guess, was it merge? So we did a join based on a common field in 2 of our data sets. So this is a source of confusion for many students, merge and join. And the reason is that what we know as join in ArcGIS, QGIS, when you join 2 tables to vector data sets, is actually called merge in Panda world. So merge is joining 2 data frames, geodata frames, based on a common column. But join, which we are going to use now, it's the same thing, but it's based on the index column. Now we will see an example and it will make more sense. So yeah, so now we are going to join this geodata frame we got from Nomina team with the original TXT file we had, the CSV file, based on the index. So because we know they're in the same order, so that should not cause any problems. But we will get back to this and I will explain a bit more. But let's do this first. So I'm going to do the join, and I will store the output in geocoded underscore addresses with ID. So I'm doing the join to add the ID to my geodata frame. So that's why I'm naming it this way. So the output of geocoded addresses is the geodata frame where we did the geocoding, the result of geocoding. And then what I'm going to do is to do a join with my original data frame, which was addresses. So this is how you do a join in pandas or geopandas in our case. Doesn't make difference. So then I want to look at what I get as the output. So I'm just going to copy the name of the output and put it here. So now the problem is solved. So we did a join. This was the output of the geocoding, this part. So this is the output of the geocoding. We had the geometry, we had the addresses. Then we did a join with our original data. So these 2 other columns are also added, ID and ADDR. And the join was done based on the index. So let's check the type of the output. It is a geodata frame, no surprise. We have the geometry column and everything. So one thing to note here, when you're doing a join, you're joining this to this one. So if the first parameter, if the left table or geodata frame is a geodata frame, the output will be a geodata frame. But if the left side is a data frame, and the right side is a geodata frame, the output will be a data frame. So even if the geometry column is there, it won't be automatically a geodata frame. Then you should just define it as a geodata frame. So take a minute and try this. Just add a new cell here and do this the other way around. So join addresses with geocoded addresses. So put addresses on the left and check the type of the output. You will see that it's a data frame.
Question for the merging and joining. As far as I know, like in GIS, a merge is basically just gluing two tables together, right?
Yeah.
Can you do the same in Python? Where you like not joining based on any column, where you just say I have this, and I know it in the same order, so it fits, so I can just put them together?
Well, that's basically the concat. Yeah, you can do it. Yeah, that's concat. So the term is different. Like merging, what is merged in GIS software is concat in pandas. And in GIS, it's a bit like they have made things easier. So like if there's mismatch between columns, it kind of you can handle it more easily. With pandas, you have to make sure things match. But yeah, that's the source of confusion. Like the terminology is a bit different between GeoPandas and the software we are used to. So did you test this the other way around? And you see the output has the geometry column, but it doesn't automatically become a geodata frame. So if you want to have the output as geodata frame without taking any extra steps, then just make sure the left table is your geodata frame and the right one can be the table. So that's one thing. Yeah, so now that we did the geotagging and we haven't added the ID field, let's just save the output. The code is already typed in. So we are going to save it in our data directory as addresses, which is a geopackage file. Okay, so we are going to use this geopackage later on during the lesson today. So I have added an example here comparing join and merge. So again, I've said it 5 times already, but I will say it one more time. So when you are doing, and this is GeoPandas, so don't compare it with ArcGIS or anything. In GeoPandas, or pandas, if you are doing a join, you don't need to say what column the join is based on. So it's only row by row in the same order. So it's based on the index of your table. So it is a bit risky. If the order is a bit off between the two, it will just join them. So it doesn't check if they are corresponding. So do this only if you are sure there are equal number of rows in both data sets and they are matching in order. If there is a mismatch, then the output will be just not correct. But if the output, if you have a common field between two tables, for example, you have the ID field in both your data set. There's an example here. So you have an ID field in both of your data sets. They can be data frames, they can be geodata frames. So you can do it just using join like we did now. Or if you want to do a merge based on a common field, then you have to provide the name of the column that is common between them. So in this case, you say on ID. And this is something we saw in the first period. And if you just provide one parameter on ID, it means that in both your data sets you have the ID column. If the name of the column is different between the two, in the first one is ID capital and the other one is ID with the small letters, then you can say on right, on left. So providing different column names for the two data frames. Yeah, so is this clear already? Yeah, okay, great. So now we have our data ready. The addresses are geocoded. And now we will continue with the other things. Later on, we will use this to do spatial join. But before that, let's work a little bit with spatial queries. And the first thing we are going to look at next is pointing polygon queries. So this other notebook. Okay, so it seems like a simple process to check whether a point is inside a polygon or not. And we know it's a very common thing to check in GIS. One example of it is just, okay, one example. We have playgrounds. We have a data of playgrounds in Helsinki. So they are as points in different parts of Helsinki. And we want to check whether they are in green areas. And you have this other land use data coming from some source. They are polygons of green areas. So if you want to check which of these points, these playgrounds, are within a green area, then this is what you do. You just make a special query to see if each of these points falls into those polygons representing green areas. So this is a very common thing we do in GIS. So have you ever thought about how this is actually done? Like, with, in QGIS, ArcGIS, we just click a button, we get the output. But what is the algorithm behind? Can you come up with a way of checking that? So you have one polygon. It can be any shape. And then you have points. So mathematically, how do you think you can? And don't Google. So just use your own brain. Mathematically, how can you check if this is inside or outside this? There are a number of algorithms how we can do this. One of them is fun, and it's the most common one, actually. How would you check that? Where did I put the microphone? Oh, here it is. Yeah, let's give you a microphone. Yeah.
You could, I don't know if it works mathematically, but you could try to figure out if there's a distance between them. If it's inside, is it?
Yep, so if you get the distance, if it is here, you get a distance because it checks it with the outline of the polygon. Then it's hard to know if it is inside or outside. That's the problem. Any other ideas? Okay, so there is one algorithm that is used very often, so you don't think about it, but it's happening under the hood when you're using ArcGIS, or even here today we don't do it because it's done already. And it's called ray casting algorithm. So it's very simple and effective. That's how you should try to solve problems. So if you just cast a ray, like a beam of light or whatever, to every direction where it intersects with the polygon. If it is outside the polygon, it will intersect it in even numbers. So here it's intersecting this twice. If this point was inside, it will intersect your polygon odd number of times. So it can be 1 if it is just a simple shape. If it's a weird shape like this, it will be 3 times. So this is how it works actually. Like ArcGIS, QGIS, the same library. They're using this ray casting algorithm, which is very simple but effective. So on the course's website, I have put some image that is better than my drawing. So it works like that. Yeah, but this is very low-level thing. We are using a GeoPandas libraries, Shapely, which does this under the hood, so you don't have to think about it. But I just thought this would be fun to know how it works. And this is rather easy to implement using Python. So if you are curious, you can just test your understanding and see how you can do this with Python. It will be a fun practice. But yeah, so that's basically what is happening, and this is provided through Shapely. Shapely is a library we saw already on the first week. We worked with you even last week again. And yeah, so this is provided by Shapely, and since GeoPandas uses Shapely, we can do this easily with Shapely. So there are 2 ways of checking whether a point is within a polygon. So there are two functions for that. One is called, and the names are quite intuitive, so within and contain. So if you want to check if a point is within a polygon, then there's a function called within. If you want to check whether a polygon contains a point, like the other way of comparison, the other way of looking at it, then there's a function called contain. And they do the same thing as just the other way around. So can you think of examples where you would use within, where you would use contain? That's one example. But programmatically speaking, imagine you have a lot of points and you want to check whether they are within the green area or not. Then you have probably a for loop going through your points. Then you check whether they're within that polygon. If it is the other way around, if you want to check whether those polygons contain any points, which are playgrounds or anything, then you do the opposite. You have a for loop going through all your polygons, checking whether they contain those points. So it depends on your programming logic, what you're trying to do. But both of them essentially return the same thing. So yeah, so let's get started and do this. We import Shapely geometry. So we first work with Shapely, then we will see how we can do it within GeoPandas. So from Shapely, I'm importing the geometry class. And I'm defining two just random points somewhere in Finland, as you can guess from the coordinates. So let's just run this and define our points. And I'm also defining a random polygon here. The coordinates are already typed in, so you don't have to do anything except running the cell. Let's print the points to see the 2 points and the polygon to see if it is defined well. We have the Shapely geometries, all looks good. So now we can start doing the special query. So first I'm trying to try within. So I want to see if point 1, which I just defined, is within the polygon I defined. And this is a binary function, so the output is binary. So you get either true or false. It's a Boolean output, so it is true. So point 1 is indeed within the polygon. Let's try it for the other point we defined. So point 2 within polygon. So we can see the output is false. So the second point we defined is not inside the polygon. So let's try this the other way around using contain. So I want to see if my polygon contains point 1. So as you can guess from the first example, this should be true. And let's try this now for the second point. And this is false. So you can check it either way, depending on what you need to get as output. So this is on Shapely level, on geometry level. Very often you have a bigger data set. You're working with GeoPandas, so you don't have to do it directly with Shapely. So this is how we do it in GeoPandas. So let's run this cell to define the directory to our data. So next we are trying to work under our data directory. We have a vector data set containing the Helsinki city districts. This is from 2021, but I don't think it has changed since. So it's a polygon. It's a vector data, the polygons showing the Helsinki city districts. So let's just run this to load our data. So this is what it looks like. You have name of the different districts and their geometry. Yeah.
This error, when you get there, I also get it from time to time. And do you know why?
Yeah, this is something about the CSC environment. So if you try it locally, it doesn't happen. It's some database thing, but it doesn't seem to affect the output. Yeah, it's just annoying. I sometimes run it twice not to see it, but it's not affecting the output. Yeah, it's because of some CSC thing. Yeah, so now the data is loaded, the city districts. If you want to see how it looks like, feel free to try to plot it, but we are going to do it soon. Okay, let's just look what it looks like before we continue. So city districts, and then I'm using .plot to just simply map it. So this is the vector data we just loaded, districts of Helsinki. So now we are going to continue working with the addresses that we geocoded in the first part of the lesson today. And we are going to check, just as an example, whether they are located within a certain district of Helsinki. So the district we are going to look at, I guess, is this one. It's the southern district of Helsinki, the Eteläinen district. So we are going to do a point in polygon query to see which of those points are inside this district. So let's run this cell. So you know already what this is. We are just selecting that one polygon, that is the southern polygon, southern district of Helsinki. So simple pandas. So now we selected just this one row, which is that one polygon. Next thing I'm doing is loading the addresses data. This is the data we created in the first part of our lesson. Yeah, so now next thing I'm going to do is plotting. And so far we have plotted only one layer, just using .plot. Now we are going to add several layers to our map. This is something that we will revisit in full detail on week 6 when we do the visualization. But now let's just quickly do it. When you have multiple layers you want to add to your map, and again, this is something we will revisit later. Similar to what we have seen in the first period, you define an axis. So this is powered by matplotlib. That's why it looks familiar to you. So first we define an axis. I'm plotting the city districts, and I'm applying a phase color gray to it. Next, I'm going to plot the southern district, so the one that I selected. And this time I'm adding it to the same axis that I defined up here. And then I'm applying a phase color red to highlight the one that I selected. And then I'm adding the addresses plot. I'm plotting the addresses, adding it to the same axis. So these are the points that we geocoded. And I'm using the color blue, and I'm applying a marker size 5. Now let's just quickly do this, and we will get back to plotting in a few weeks. So this is now our output. So we made a simple map. So we added the old districts, then we added a second layer as red, the district we are interested in, and the points we have geocoded. So we can see that some of our points are inside this southern district of Helsinki. So visually it's easy to see it, but now let's try and do it like programmatically. Yeah, so let's start doing this. So I'm using the addresses points, and I'm testing whether they are within the southern district that I defined. So we already defined this southern district. Well, we selected it from our data. And here I'm pointing specifically to the geometry of that polygon, and I will explain to you why I'm doing this way. So here I'm pointing to the geometry. So what this does, it goes through all your rows of addresses. We have 34 of them. It checks whether it is within that geometry, and the geometry was that southern district of Helsinki. So I have used, like I've specifically pointed to the geometry there. Now test this. Remove this, just spend 30 seconds and try this, and we'll do it together. So remove this at and 0 and just provide the geometry column to see what you get as the output. And guess what is going wrong or what is going differently. So instead of providing that one cell, provide the geoseries, that whole column. So did anyone get the output? So what does it look like?
It's just the first value is returned as true and all the others are false.
Yeah. So did anyone else manage to reproduce that? Yeah, so some of you. So that's, do you have any idea what is happening, why you're getting that output? So what is happening? If you point specifically to that geometry, it checks all the rows of your addresses. So you have 34 rows with that one geometry. But if you provide the whole column of geometry, if you remove this at and 0, it's going to look at all the geometry. So what it does is a pairwise comparison. So if these are my addresses and these are my geometries, it just compares them one by one, like this. In this case, we only have one geometry, so we don't have these. So what happens, it works for the first one. For the other ones, there is no corresponding geometry. So you get false as output. So if you provide the whole column, not pointing at one specific geometry, it's going to do it pairwise. So index 1, index 1, index 2, index 2, index 2. So it goes row by row. And in this case, because we have only one geometry, you get false. But if you point at a specific geometry, then it just checks all of them with that one geometry. So that's the difference. Just be careful with that. Yeah, so we can see for some of them it's true, meaning that they are inside the southern district of Helsinki. Some of them are false, meaning that they're not there. So this is probably not super useful for you. What you want to do is to, for example, make a selection, only keep the points that are within the district of Helsinki, southern district of Helsinki, and you can just easily do that. So you can just provide this here. So before we have seen similar things, putting conditions in the first period. Because this returns a Boolean value, true or false, it can be used for selection. So if you do this, if you run this, it's going to just keep the rows for which the output of within was true. So it will only keep the points that are within the southern district of Helsinki. And so there's a handful of them. So next, we are going to visualize this. So again, we are adding multiple layers to our map. That's why I'm defining an axis first. I'm adding the city districts, all of them as gray. I'm adding the southern district as red to just kind of visually highlight it. And then I'm adding the addresses that are within the southern district, the ones that we just selected here, to our map. I'm applying color gold. You can use other colors. And a marker size of 5. Yeah, so this is the output. So does it make sense?
One question to this mask array. So basically, when this expression in the parentheses, in the rectangular one, when it's true, then the whole row gets aligned to the new data frame, southern district.
Yeah. Yeah, so there you can have any condition. In this case, is this within. It can be something that returns Boolean value. Yeah. So it goes row by row and checks that. Okay, so let's move on to the next thing, which is intersect. So this is again similar. So we are still working with the spatial queries. Now in the example we just completed, we were looking whether a point is within a polygon or whether a polygon contains a point. Now we want to try something with lines. So with lines, it's not about being within or containing, but you want to see if two lines are, for example, intersecting or are they touching each other. So this is what we're going to do. Now we just define a couple of random lines with some random coordinates, and we are going to test a few things with it. So with intersect, and so these are the two things we are trying now. Intersect and touch. So with intersect, they can intersect in whatever way. It's not picky. So if they touch each other, if they overlap each other in any way, the output of intersect is true. But touches is a bit picky. So they have to they shouldn't be overlapping each other. They should be just touching each other at one or several points. And we will see an example of that. So this is an example. So depending on what you are trying to do, you may decide to use either of them. So again, this is something coming with Shapely. So let's define our geometries. So we are going to define two line strings with some random coordinates. And to see if they intersect each other, it's very simple. So I want to see if my line 1, which I just defined, intersects line 2. And the order of this doesn't matter, of course. So as simple as that. You can see if the two lines are intersecting with each other. Let's also see if the lines are touching. Line 1 touches line 2. And these are binary functions, meaning that they return Boolean value to you. So they are also touching. So I want to now quickly visualize this. To visualize them both at the same time, I'm just defining them as a multi-string, and then I'm going to so let's just run this. So this is just to visualize them at the same time. I just put the two lines together as a multi-string. So these are the two lines. This is one line. This is one line. So this is what we were checking to see if these two lines are intersecting or touching each other. So you can see that they intersect. As I said, intersect is not picky, so it doesn't matter how many times or how much, to what extent they are overlapping. But with touch, it has to be just touch. They shouldn't be like overlapping with each other. So let's test another thing. So line 1 touches line 1. So I'm checking with the same line. So if I'm testing if it's the same line is considered touching itself. So line 1 touches line 1, false. So the condition is not met. So as I said, they should be just touching in one or few points. If you check whether a line is intersecting itself, because they're completely overlapping, the return of touch will be false. But if you do the same thing with intersect, I said it's not picky, it will be true. So let's see, line 1 intersects line 1. Yeah, so depending on what you're doing, and now we are going to look at this again in practice when we are doing the spatial join, because there you have to define a condition. So you should know what touch means, what intersect means. There are a few other ones, and we will see some more. And in the documentation, you can see how they work. But yeah, this is how it works with intersection and touch, if you're working with lines or polygons. So let's continue with the spatial join, which is the more fun part of the lesson today, because it's something we use quite a lot when doing GIS. So we already looked at some of these predicates. So when you're doing a special join, you're doing it based on a special query. So if a condition is met, then the join would happen. So if a point is within polygons, then do the join. So bring the attributes of that polygon to my points, for example. So there are a number of conditions you can choose from. These are the most common ones, but if you check the link here, there is more that there might be something you need. But very often we are checking if objects are intersecting with each other, whether a polygon contains another polygon or a line or a point, whether something is within something. So some of the things we just looked at today. So you can use these conditions to do a special join. So when you're doing this in GIS software, in ArcGIS and QGIS, usually there's a drop-down list. You choose what is the special join condition or predicate. So yeah, so there's a list of them available. These are some of the most common ones. And these are binary geometric predicates. The output is Boolean, like we saw already in our examples earlier. So it's true or false, and depending on whether it's true or false, the join will happen or not for that particular line in your data. So that's one thing. So if you're doing a special join, there are a couple of things you need to decide about. So one of them is the predicate, the condition based on which you're doing the join. We saw a few examples of that. The other thing you should decide about is the type of join. And there are 3 types of join you can choose from. One, so it can be a left join. So in GIS software, in ArcGIS, QGIS, we have the same thing, but it's not said explicitly. So you probably have done this. If you're joining one layer to another, it makes a difference which one it comes first. So do you remember how to join in QGIS or ArcGIS? So you right-click on one of your layers, for example, in ArcGIS, then you choose join. You join it to another layer. So the one that you select first becomes your left geodata frame. The other one you're joining to the first one is the right one. Here, we don't have a user interface, so you have to explicitly say which one is the left one, which one is the right one. And here's the difference. So if you choose the join type left, it keeps all the records of the left data frame. So if I join A to B, A is my left, B is my right. If I choose the join type left, it will keep all the attributes of the left, which is A in my example. And if there is no matching row in the B, in the right one, then it just puts blank, but it keeps the column, keeps the row. And it keeps the left geometry. So if you have, both of them can be, both of them are geodata frames, they're vector data. So it keeps the output is the geometry of the left one. So if you use right, is the opposite. So it keeps all the column of all the rows of the right data frame, and it keeps the geometry of the right one. And then there's another one that we sometimes use, and that's inner. So inners is just whatever is common between them. So in ArcGIS, for example, when you do the join, it asks you, there's a box you can tick that should I keep all the rows or only the matching ones? So this inner is the matching one. So if you tick it, if you choose it, it just keeps the matching ones. And if you use inner, just remember that it will use the geometry of the left one. So remember that. If you want to learn more about this, again, there's a link here in the PyGIS book, so you can learn a bit more. But it's simple, and now we go to the example, so it starts to make a little bit more sense. Yeah, so again, as usual, let's define our data directory. Let's just run this cell. Then let's go and run the second cell. So we are getting so what we are doing here is the example that I asked you about at the beginning of the class. So we have the addresses that we have geocoded. Now we want to get the population density around those points. So around those home addresses, home locations. So I'm getting the population data from WFS through the Helsinki Region Environmental Services. So I'm not downloading any data. I'm just getting it from WFS, just reading it directly from there, specifying what coordinate system it is using. At the same time, I'm also reading the addresses. This is the data we created at the beginning of today's lesson. So now this should be loaded. Okay, so now before we continue, let's take a quick look at our data to see what we just imported. So let's look at our population grid. This is what we got through the WFS. We got head. So this is what we have. This is probably, has anyone ever used this population grid data in Finland? It is a common data, so depending on what you're doing, and you can download it from like PyTuli, for example. So we are going to plot it later on, so you will see what it looks like. So it's a grid covering the whole country, and it has population information. So you see, these are some of the columns that are included, come with the data. So you have population, number of inhabitants, and a number of things, like population by different age groups. Yeah, so a bunch of information. We don't need all of them, so we are going to keep the number of people living in the grid and the geometry column. So this is all we need. So I'm going to reload the data and just keep only these two columns. At the same time, I'm going to translate one of the columns. So from Asukkaita, I'm going to translate to population, so it's easy for all of us. And this is something we have done many times, defining a dictionary and using it for renaming my columns. So now that we did this, we want to calculate the population density. So this data comes, so it doesn't have the density, it has the number of people living in each of these grid cells. Yeah, and the size of the grid, this data set comes in different resolution, but the publicly available one is 1 kilometer by 1 kilometer. So this is simple math. I'm just calculating how the population density. So I'm just dividing the number of people living in the area in this grid cell by the size, by the area of the grid cell. So the grid cell is 1 kilometer by 1 kilometer. That's why I'm dividing it by 1 million. I want to get it number of inhabitants in each square kilometer. So simple mathematics, getting the area, dividing it by 1 million, and yeah, so population divided by area divided by 1 million to get it in square kilometers, because it comes, well, the area will be in meters. So simple mathematics, and I'm storing it in this new column called population density. So, and a couple of things here. So probably it looks weird for you. I'm writing 1 million like this. And that's, you don't have to write it this way. It's just a good coding practice. So if you have many digits, it's like a divider. You can put underscores every 3 digits to just make it more readable. So you can also go without it, but it's a good practice. So it's a separator. So when Python sees that, it knows what you mean. It knows that it's just 3-digit separator. So if you have very long numbers, like in this case, we have 1 million, it's a good practice to just put underscores. It makes it a bit more readable, especially if you have even more than this digits. So here we have like 7. It's not so many, but yeah. Another good coding practice, we already saw in the first period that if you have a very long line of code, like in this case, it's quite long. So if you wanted to write everything in one line, it's fine, but then it's just hard to read. That's why I've broken it into different lines. And if you have a mathematical equation and you're starting a new line, here we have a mathematical equation, we have division. It's a good coding practice to start the new line with the sign of that mathematical operation you're doing. So of course I could have put this division sign up here, then continue here, but it's a good coding practice to start the new line with the mathematical operator. It just makes it more readable. So we do the calculation, we store it in this new column, and then we get the data head, the geodata frame head, to see what we get as the output. Yeah, so now we have a new column added to our geodata frame. So we have the columns that we already had, population and geometry. And now we added this population density, which is the number of inhabitants per square kilometer. So that's what we calculated. So now that we did this, we want to do the spatial join. So one thing to be very careful about when doing any spatial query, so it can be those like shapely things like intersect, touch, within, contain, or here it's a bit more higher level doing a spatial join. Be super careful with coordinate system, because when we are working with software like ArcGIS, QGIS, we have gotten a bit like lazy, because they take care, to some extent, they take care of the coordinate system on the go. But when you're working with GeoPandas with Python, no one is taking care of that for you. So when it's doing that, it's just working with pure coordinates. So it doesn't know what coordinate system they are in. So if you have your multiple data in different coordinate system, GeoPandas is just going to look at the numbers of coordinates. Doesn't know what is the coordinate system. It's not going to do that for you automatically. So if they are in different coordinate system, of course, coordinates don't match. So you will not get anything as output. They probably do not overlap. So whenever a coordinate system is always important, particularly when you're doing special queries. If they are in different CRS, it's not gonna work. So that's why whenever we are doing something like this, we have usually this assert line, checking if the coordinate systems are matching. So let's run this, and we can see the CRS are not identical. They're different. So you can choose what coordinate system you want to use for your work. I'm going to use the coordinate system of my addresses. So I'm taking the population grid to the same coordinate system of my addresses. So I don't need to even type in the name of the coordinate system. I can just use addresses.crs. So now my population grid should be in the same coordinate system as my addresses. So I'm now ready to do a spatial join. Okay, so let's start doing the spatial join. The output you will get will be another geodata frame. So I'm going to give it a name to store it under a variable name. I'm going to name it addresses with population data. So as a reminder, we have points. These are home locations we geocoded. We have population data. We are doing a spatial join to get the population information to my points. So I'm going to name the output of my spatial join spatial addresses underscore with population data. And this is how you do the spatial join. So this is your left geodata frame. So the order matters here. So addresses is the left one. So on the addresses, I perform spatial join, and this is how you do it, S-join. The next thing you provide is the right geodata frame. So remember, left, right. So addresses was the left one. Population grid is the right geodata frame. Remember, another parameter we need to define for doing a spatial join is the type of the data join. And remember, there was left, right, and inner. So which one is the right one to use here? What is the output we want? Yeah, I heard one correct answer. Left or right? So remember, what is it that we want as output? We want the points. We want to know the population around the points. We don't want to get the grid, the population grid. We want to have the points with new columns added to it. So this is the data I'm interested in. So I'm adding something from this to this. So the join type I'm using is left because I want to keep the geometry of the points. I don't want to get the grid. So this is the parameter you provide, how, and I'm going to say left. So this is how you define the type of join. And then the next thing you need to define is the predicate. So it's the special query. So the condition you want to define for it to work. So I'm going to use within. So I will see if the point is within a certain grid cell. If it is, then I will read the population data from that cell and add it to my point. So that's all you need to do a special join. Then I'm going to just add the name of the output to see what the output looks like. So addresses with population data. So let's just look at the head. Yeah. So now the join is done. In your data you have 30. It's coming from addresses, so I guess we had 34 rows, 34 addresses, so the output should have 34 rows. And then we have gotten the population density. So the population density was in the grid data. Wherever it was matching with a grid cell, it read the population density and added it here. And in some cases, there is a missing value because the point did not fall into any grid. So because we use left, it keeps the point, but if there is no matching grid, it just returns null value as the output. So which was the case in at least one of the rows we can see here. So this is how you do a special join. So note that when you do the special join, it adds a new column. Well, it adds the columns from the other data, but also it adds this index right. So it's the index value of your other geodata frame. So if you have used how as right, then here you would have got an index left. So it keeps the index value of the original data. So if you want to join or check with the original data, you know which index it's coming from. So this is a reserved term. If you already have a column named index right or index left in your data, and you try to do a special join, you probably will get an error that the column already exists. So if you get that kind of error, and if you retry, if you do multiple special joins, you might end up with a data that has that column already. So you will get the error that the column name exists. So in that case, just rename it or do something to avoid the conflict. So yeah, so be careful. This is an error that you will probably see at some point if you do special join a lot. Yeah, so this is the result of my special join. Next, I'm going to plot to see what I just produced. So the code is already typed in. Again, I'm going to create a map. Yeah, so I'm going to add addresses with population data, and I'm going to add the number of, so I'm mapping, well, we will get back to this visualization and how this works, but just briefly to show you what is happening here. I'm plotting my addresses with population data. I'm providing the figure size for my output. This is the column I'm visualizing here. So the population density. So there are different color maps you can use, different shades of red, different shades of blue. There are many of them to choose from. And again, we will revisit this later on. I'm just now using different shades of red to show different population densities. And then because we have a lot of values, it makes sense to classify the values. So I'm using quantiles to classify the outputs. And we have a whole lesson about data classification, so we will get to that later. But for now, I'm just using quantiles for visualization, marker size 15, and legend true. So this is how you can add legend to your maps. And then if you want to add a title to your map, to your visualization, you can just write something here. Let's run this and see what the output looks like. So this is what we just created. So it's a So these are the points we geocoded. And the darker it is, the higher population density we have at those points. So you can see places which are in the center, there's higher population density, so they appear a bit darker. And of course, you have the legend here, so you can check what are the different categories, different classes. So this is a map of the population. Yeah, so let's just run this. So this is a map of the grid, and as I said, this is a data set that is openly available to us in Finland, at least at 1 kilometer resolution. So it's a grid. This is just from the Helsinki area, but it's available from all residential areas in Finland. So if you have any need for any, I don't know, population-related calculation, you can just get this data from WFS or Python or probably other places. Yeah, so it looks like this. So this is a visualization of the grid data with population. Darker areas are areas with higher population density. And yeah, so if you want to save the output, you can do that. So let's just run this cell, and this will save the output as a geo package. So later we are going to see this more, but geo package is not like shapefile, so it's not just one file. So it's a combination of things. It can have a combination of vector and raster. It's more like a geodatabase, as you might know from ArcGIS. So that's why you can add multiple layers to a geopackage. So one geopackage can have multiple layers of data. So you can think of it as geodatabase if you have worked with ArcGIS before. But we are going to look at that later on during this course. Yeah, and that was it for today. Then you have exercise 3, which is related to what we did today. You will work with a special join and related things. And yeah, from this week on, we don't have auto-grading. How was your experience with auto-grading? Did you like it? Was it better than what we had in the first period? You raise your hand if you liked it better than the first period. Yeah, okay, so most of you liked it better. You didn't like it. Not really. Okay. So yeah, so it's actually, we only have it for 2 exercises now, but hopefully for next year we will have 4 more. So from this week on, you will not get this automatic feedback, but we will be grading you weekly and you will get feedback from us. Yeah, other questions?
What if you want to join several data sets at once? Like the problem with the that it says the index right already exists. Can you join several at once? What would it say then?
Special joins works 2 at a time. You always join one thing with one thing. So if you want to do multiple, then you have to join one thing, then join that new layer to the next one. So in that case, you have to take care of the name. Either rename the index right, index left you have, or I don't remember exactly, but there's a way to also tell the function to use another name. So don't name it index right or index left. You can specify what it can be called. But you can check from documentation. But the special joins works for 2 layers at a time. Yeah. So if there are no questions, then that's it for today. See you next week.